So, good morning, everyone. Welcome to HICE seminar. Today, we are pleasure to Théo, a PhD candidate from aeronautical sphere and India. He was speaking on deep learning for exoplanet detection in high contrast image. Théo, please take it.
Hi everyone, thank you for having me. So today I will tell you about the topic of my PhD, which is deep learning for exoplanet detection in high contrast imaging. So can you see my screen?
Yes.
Okay. Okay, good. So first, a few words about me. So I'm a fourth-year PhD student at INS and INRIA in France. I'm supervised by Jean Ponce, Julien Méral, and Olivier Flasser. And I focus on applying machine learning techniques to physical problems, and especially direct imaging related to astronomy. So in this talk today, the talk will be divided into three parts. In the first part, we'll see how to combine deep learning with statistical method for exoplanet detection. Then we'll see how to go beyond observation-dependent approaches to leverage a large database of observation. And finally, we'll see how we can refine the statistical model to leverage correlation, physical correlation in the data. So all these works have been done with my collaborators, so Olivier Flasser, Julien Méral, and Jean Ponce, my supervisors, but also Maud Langlois and Anne-Marie Lagrange, astronomers with whom we collaborated a lot in the last 3 years. So I'm sure you're very well aware of the method for detecting exoplanets, but I will do a quick recap. So in this talk, so we have two categories of method: indirect method and direct method. In this talk, we will focus on direct method, direct imaging particularly. So there are two main challenges in direct imaging. In order to be able to image an exoplanet that is close to its host star, you need to have a very high angular resolution because both objects are quite close and very far away. And you need also to have to be able to achieve a high contrast. So contrast is the flux, the ratio of the flux of the exoplanet with respect to its host star, and it's quite challenging to detect exoplanet this way in terms of contrast. So to do that, we need large telescopes, and also we need dedicated optical devices. So the main issue that we have with this kind of imaging is that we image exoplanets through the atmosphere, which is a turbulent medium. So the refractive index is not homogeneous, which causes speckles in the observation. One way to mitigate this issue is to use adaptive optics. So you detect the wavefront distortion and you correct it in real time. You can also use a coronagraph to reduce the glare of the star so that exoplanets next to it will pop out better. And then you need also a post-processing algorithm to make sense of this data and to leverage the correlation that you know exists in the data. If you are able to do that, you can do a lot of great science, but it's challenging to do all of these steps. So if we look at an observation in direct imaging, what we have is at the center a very bright signal that is caused by the host star. So that's the speckle. So there is a very high dynamic range between the intensity in the center of the image and in the outer region because of the strong signal of the star. And when we capture an observation, we capture several frames. And what we observe during this frame is that the signal of the star is not exactly static; it's quasi-static, so it has a slight temporal evolution, which makes it very difficult to subtract. And that's the main issue with detecting exoplanets in direct imaging. So if the exoplanet is detected in the outer region, it's easier because you don't have the speckle pattern hindering the detection. But if you're close to the star, it's much more challenging because of the strong nuisance component of the star. Here we can see that there is an exoplanet, but it's very faint. It's hidden in the noise of the image. But when you combine a temporal series of images, you are able to lower the noise, and so the signal of the exoplanet will appear more clearly. So when you take observations this way, this is the kind of data that you have. So we can see that during the temporal evolution, the pattern of the star is quite different from one observation to the other. It's caused mainly by turbulences in the atmosphere. So things that are out of the control of astronomers. But what you can do to improve the signal ratio of exoplanets is to use the dedicated observing strategy. And one strategy that is very efficient is angular differential imaging. So the idea of angular differential imaging is that when you observe an exoplanet or a star at night, the Earth is rotating, so we can leverage this rotation of the Earth to induce a difference of behavior between the speckle pattern, that is a nuisance component that we want to get rid of, and the signal of the exoplanet. So if you take an observation with the field rotator of the telescope turned off, you obtain a static PSF, so the PSF of the star will not rotate. But what you observe is that the field of view will rotate. So if there is a companion next to the star, it will follow a trajectory that is known in advance and that can be used for the detection. So here I represent it very quickly. So when the Earth is rotating, the star is still at the center, but the exoplanet is describing a trajectory that is known. And the goal is to derive algorithms that are able to detect this exoplanet among the noise. So what are the main methods to solve this problem? The first class of method is a subtraction-based method. So in these approaches, we try to construct what's called a reference PSF. So we try to reconstruct what's a model of the stellar PSF that will then be subtracted, so that hopefully there is only the signal of the star remaining. So there are a lot of methods that work this way. Another kind of method is a statistical-based method. This time we try to model statistically what happens at the scales of pixel or patches. And so then once this local model is done, you can derive a detection map of the whole field of view. And there is also learning-based methods, so using machine learning techniques to solve this problem. And so what we try to do is to combine a statistical-based method with learning-based method, because statistical-based methods are very efficient in the outer region of the observation, but they struggle a bit more in the center, as we'll see. So first, in this first work, we will build a method that leverage the statistical model of PACO. So I will first explain quickly what is PACO and how does it work. So in PACO, the method divides the observation into patches of a fixed size, and then it models each temporal series of patches as sampled from a multivariate Gaussian distribution. So this is a local model. So there is one model for each patch in the image. And what they do is they first fit this local model for each patch. So they compute the mean and the covariance matrix for each patch with some regularization, but I will skip that. And then once you have this model for each of the patch, you can combine all of this all of these local models and derive a global detection map So here you can see synthetic exoplanets that are injected in observation. And when there is an exoplanet, the SNR, the signal to noise ratio, is higher, and that's how you detect exoplanets. What we do is that we build a learning approach on top of the model of PACO. So as I explained previously, PACO is done at the scale of patches. So we want to leverage this statistical model because it's still very efficient and it works quite well. But it only captures local correlation of the data because it's built at the scale of patches. So we want to be able to reuse this model, but to build something more on top. So what we do is that we do a whitening of the data with the statistical model of PACO. So when you do whitening of the data, you basically remove all of the correlations that are captured in the statistical model. So if your statistical model is perfect and it captures everything very well, when you whiten the data, you obtain some white Gaussian noise. So there is no more information left because everything has been captured in the model. But when the model is not perfect, when you whiten the data, there will still be artifact remaining that results from the fact that the statistical model did not capture everything in the data. So that's the assumption here. We first do a first preprocessing step where we whiten the data with the statistical model of PACO. Then we align the data, so we align the signal of the sources. So we derotate the data, and then we feed this data to a convolutional neural network, so a deep learning model that takes as input the whitened data aligned, and that will output a binary detection map, so probability of presence of an exoplanet for each pixel. But
Theo, all right,
yes.
question. When you're whitening the speckles, how far is this applying, like in the immediate vicinity of the PSF or the larger image?
So it's for every patch in the image. So it's both in the speckle region and also it works also in the outer region when there is no speckle. But there is still in this region when there is no speckle, the covariance matrix will be diagonal or almost diagonal because the pixels are independent. The noise in the pixel are independent in the outer region mainly.
Yeah, my sort of big science question is like, is there concern that this can erase faint signals from planets?
Yeah, absolutely. That's a concern. That's one of the main limitations of this statistical model is that when you feed the model, you capture part of the exoplanet signal into the parameter of the statistical model. And so then you don't detect the exoplanet if you have already captured this as a speckle signal. So that's self-subtraction. That's an effect that is very well known in all this method for ADI processing. We'll see that with deep learning we are able to mitigate this issue, but it's still a big concern with this kinds of methods.
Okay, yeah, thank you.
You're welcome. Okay, so once we have whitened the data, we feed it to a neural network, but we need to train this neural network. So to do that, we inject fake exoplanets in the data, and we train the neural network to retrieve these faint exoplanets. So that's the main idea, but there is a small detail with this process, is that you're not sure if there is an exoplanet or not in the data because maybe there is an exoplanet, but it's too faint to be known by other methods. So what we do is that before injecting the synthetic sources, we shuffle the frames temporally so that we destroy the coherence of a putative exoplanet that is unknown. So when we do that, we can inject the data, the synthetic sources, and then train the model to retrieve them. We can do that because the statistical model is not, it doesn't depend on the order of the frames because it models the collection of patches are sample from a multivariate Gaussian distribution. but there is no assumption of order, so you can shuffle the frames and it won't impact the statistical model. Okay, and so to do the training, you need to give you need to define the training loss that will be minimized during training to update the weight of the neural network. And so the loss that we chose here is a dice loss. It's a loss that is usually used in computer vision for segmenting images. So yeah, we use this one here. So now for results with this method, so we compare several baseline for ADI, and we see that already with this approach we are able to gain quite a bit of contrast with respect to PACO, especially yeah, a bit on the whole angular separation range, and we get closer to the fundamental lower limit of detection that is given by photon shot noise. So yeah, it works quite a bit better. Here we compare detection map that we obtain with several methods versus with deep PACO. We see here an example where deep PACO is able to detect exoplanets that was not detected by PACO. Yes. So with PACO, we have seen that with deep PACO, we have seen that the learning-based approach gives better results than learning-free approaches. But there is still some issues with this technique. Is that the algorithm is still observation dependent, meaning that you need to train a new neural network for each new observation, which is not ideal. And also, as I said earlier, we're still limited by the statistical model in the sense that if there is self-subtraction in the statistical model, so if the signal of the exoplanet is captured by the statistical model, then it will be lost, and the deep learning model that is afterwards won't be able to recover it because it will be lost in the parameters of the statistical model. So that's still some issues with this technique. And also there is still some gains to be had in the closed region, very close to the star. So that's what we try to improve in the next work. So in this work, MODEL&CO, we adopt a different approach. So there are several differences with respect to deep PACO. The first one is that we have an observation independent approach. So the model is trained only once on a large archive of observations. And we have a single model for every observation, not a model per observation. So that's already very different and quite practical if you want to process a lot of observations. So that's the first thing. Then we do also similar to deep PACO, we inject fake sources and we train the model to retrieve those sources with a few differences. One of those differences is the architecture of the deep learning model. So as we have done with deep PACO, we've seen that there was two parts. A part is that was the pre-processing of the data that was done with the statistical model. So this part was not learnable because it was only fit on the data and there was no learnable parameter in the sense of deep learning. So this part was frozen. There is nothing that can be learned in this part because there is nothing learnable. And then there is the deep learning part that comes after it. And in this deep learning model, there is learnable parameters. Here, what we do is we introduce some learnable parameters in the first part. So in the pre-processing of the data or in the part that is speckle aligned before the rotation. And this allows to mitigate in parts, not totally, but in part the self-subtraction effect, as we will see. And the way to do that is that we use an architecture, a residual architecture that is used in UNet, which is a very common type of deep learning architecture. And we want to keep the ingredients that worked well with Paco and DPaco. And what works well with DPaco and Paco is the correlation, the covariance of the pixels. So that's the thing that is very important in Paco and DPaco is the covariance matrix that you learn on the scale of patches. If you don't learn the correlation but just a diagonal matrix, it works much worse. So we want still to learn some correlation in the data, but we don't want to do that. We don't do that anymore at the scale of pixels. We do that at the scale of learnable features. So what we do is that we extract patches similar as Paco and DPaco, but instead of fitting the mean and covariance matrices directly on the pixels, we first do a matrix multiplication or linear projection. That's the part that is this part is learnable by the neural network, and then we model the correlation after the projection. So that's called features, learnable features, and we still have this modeling of the covariances in somewhere. And yeah, then we use also some nonlinear units, so some activation units, some 2D spatial convolution to aggregate information a bit larger than a single patch, but also on the neighboring patches. And so everything that is in green is learnable here. So that's weight that can be updated at each iteration of the neural network. So you can see that this is the main difference in architecture with respect to DPaco, is that the speckle line part is learnable. Then we do similarly as DPaco, we derotate the learned feature, the whitened features. We aggregate them, and we have a final unit similar to DPaco to denoise the final step of the method. And so yes, so this is just a bit the normalization, the whitening layer a bit more formally, but it's not that important. And what's also important with respect to DPaco is that the loss is different, because we saw that with when we use DPaco in practice, we had a problem is that we had to tune quite precisely the flux of the sources that we injected. If we injected too high, then the model would be too easy for the model, and if we inject too low, the model will struggle and will not converge, because the task will be too difficult for him and for it, and it won't understand what it needs to do. So in order to mitigate this issue, we used a new loss, which is basically we try to optimize the signal to noise ratio of injected sources, and this is better because if the source is injected in a region with high variance, then the target signal to noise ratio to be reconstructed will be lower, because it takes into account the region where the source was injected. So you won't suffer, the model won't suffer the same loss if it fails to detect an easy source with respect to a hard source, which makes it much easier for the model to understand what it needs to do basically. So that's the three main differences with respect to DPaco: a large database of observation, a different architecture, and a different loss. We also added a calibration procedure, because one issue that we had with DPaco is that the probabilities that were the output of the neural network were not calibrated. So here we do that a bit more cleanly. I won't go into the detail, but I can explain it later. And now we can see some results. So here we plot the output signal to noise ratio with a lot of injected sources. So we have on the y-axis the contrast, and on the x-axis the angular separation. So here with standard rotation, we can see that the results are quite similar. Maybe Model&CO is a bit better. But when we lower the rotation rate, so when the problem of self-subtraction becomes stronger, what we see is that PACO fails completely to detect those sources because, as I explained, when we fit the statistical parameters, we may capture the signal of the exoplanet, and it will impact the detection performance. Whereas with Model&CO, we can learn to avoid to do that somewhere, and we are much less sensitive to self-subtraction, especially when the parallactic rotation is smaller.
So what's the detection score? Is that signal to noise of detection?
Yes.
Okay.
It's SN. Yeah. So here we can see an example on a source where PACO and DPACO fails to detect it, but Model&CO is able to detect it a bit better. We can see also examples on synthetic sources. So here, sources that are in green are detected and orange are not detected. So you can see that with a rotation rate of 23 degrees, it's a bit similar, maybe a bit better for Model&CO. But when we lower the detection to 2 degrees, so very challenging, PACO fails completely, but with Model&CO, we are still able to capture those sources. Another interesting effect is that the detection performances increase with the size of the data set. So that's something that is expected, but it's still nice to verify it. We also did experiments by splitting the data set into observing conditions with the strain ratio and the thing, basically into a bad, average, and good quality of observation. And the question was is it better to train a neural network or this model only on good observation, or is it good also to include some bad observation in it? And basically, the answer is that it's better to put everything in the data set and just let the model train on everything, because that's where we obtain the best results. Okay, so to conclude on Model&CO, we saw that one of the key advantages of Model&CO is to obtain a single observation independent model that is able to use a full archive of observation. We are able to provide a gain in detection sensitivity and also to optimize the observing time, because we can obtain the same performances with less frames. So in a sense, we can shorten the observation. And we also provide a calibration procedure to obtain a probability of false alarm with each detection, which was not necessarily the case with DPACO. But there is still some issues to be resolved. Is that this model is not multispectral, but it only works for ADI, so a single channel. And there is no astrometry or characterization, so we cannot estimate reliably the flux of the source or its position.
When you say it's missing, it just means you haven't done it yet, right? Not that there is a problem for doing it? Okay.
We tried to do astrometry and characterization with Model&CO by basically subtracting the source to minimize the residuals, so something that is done also with other methods, but it was not as performant as PACO, simply doing that. Because there are some non-linearities involved, and it's hard to know when you minimize the residual exactly, because this region is very flat in the optimization landscape. So you don't really know where is the best flux that minimize the residuals. So it was not working very well for astrometry characterization. For multispectral data, we also tried some naive ways of implementing it. but it was working less well than just simply doing a PACO ASDI, which models the correlation of the PSF spectrum more accurately. So we tried some naive things, but it was not very very appropriate for this model.
Cool.
So that's the next work, which is named exomide. So in this, so what we have seen is that statistical models are good for determining the flux or for characterizing sources, so determining the flux and the position accurately. But it's not the best tool for the detection. So here we try to combine both, so to have a learnable model that can be trained at scale, but we try to still maintain the interpretability of statistical model that allows to minimize some objective or some likelihood to fine-tune the position of an exoplanet. So it will be maybe a bit clearer later. But also one other thing that is not really accounted for in previous model is that in the data there are some symmetries in the speckles in the pattern in the stellar PSF pattern. The speckle exhibits some symmetry. So if you take two opposed patches, you obtain very correlated patterns. And so we wanted to see how that could help with detection. So what we try to do in this model is to have a model that is still interpretable statistically, and the way we do that is by first. So I will first introduce the models that we use in this the statistical model that is used here. So with PACO, we had a model that is built on patches, and more precisely, what's happening is that for a given pixel, its distribution is determined by the patches that is surrounding it. So if you take two pixels that are next to each other, their distribution is only determined by the patch around it. So that's quite an issue, because first you need to fit a lot of Gaussian distribution, basically one for each pixel, one for each spatial pixel. So that's very expensive in terms of resources. And also another issue with this model is that for each pixel, it's only modeling correlations with the pixels that are in the same patch, not pixels that are located further away. So what we do in our model is that we do a convolutional statistical model, in the sense that for each pixel, its distribution will be not only determined by the patch that is around it, but by basically, for example, here, a collection of 4 patches that are overlapping at this point. So with this model, you obtain a much larger field of view for each pixel. So you can model correlations at a longer range, and also it's more efficient because you don't need to fit as many Gaussian distribution. Here we have one distribution per pixel. Here we can do one model every 4 pixels, for example. So that's 16 times less models of Gaussians to fit. So it's much more efficient. And why we care about efficiency here is that if we want to integrate it into a neural network, it needs to be quite efficient, because you will when you will feed the data through the neural network, it will need to go through this model. So each time we need to fit all the statistical model in the image, and it can take quite a lot of memory. So if the model is too complex, it won't fit into memory, and you won't be able to run the neural network at all. So it's important to have an efficient way of modeling the data. So there is this first improvement over PACO, is that the model is convolutional. And also what we do is, so here we combine for each pixel adjacent patches, but we can go even further than that. And instead of combining patches that are adjacent or overlapping, we can combine patches that are opposed, basically. So that's what I showed here, sorry. So we can have joint model of patches that are located at opposing sides of the PSF. And we can go even further than that. So instead of modeling correlations between patches that are located at basically 180 degrees from each other, we can also be a bit more fine in this model and do a joint distribution of patches that are separated by 90 degrees of rotation, because there is also some there might be some correlation also in these areas. So with this, so what is learned in this model actually is how to combine this distribution, because what I explained to you up until now is what we model, but the neural network will learn the optimal weight to combine all of those distributions. So there are still the distributions that are at the scale of a single patch, distributions that are modeling opposing patches, distributions that are modeling patches separated by 90 degrees. And also we included some larger scales of patches, because there are also some correlations, not only at the scale of an 8 by 8 pixel, but also at the scale of 16 by 16 or 32 by 32. And so the neural network learns to combine this distribution. So we'll see some results now. So here we have some results in ADI and in ASDI. So it's also by combining two bands of observation. We see already that by using the same size of patches as PACO, and just by using the convolutional model, so by using overlapping patches instead of separated patches, we can already improve the detection performance significantly. Now we add on one part larger patches. So we for each new row we add a new scale of patches in the mix of distribution, and also for the columns, for each new column we add opposed patches. So in the middle column, so in the first column we have only a single patch. In the second column we have a single patch and its opposite, and in the third column we have a patch, its opposite, and also the other patches that are separated by 90 degrees. And so we see that the best results are obtained by combining all of those distributions. So that's only the statistical part. And when we add on top a learned denoiser, so similar as we did before, we add at the end after the statistical correlation, we add a convolutional neural network to denoise the data. We can even push further the performances. So here we compare the performances with other methods in both ADI and ASDI, and we see that we are a bit more performant than other methods, and we are a bit in a tie with MODEL&CO. And also one of the advantages of this approach is that since we base the first part of the model on a statistical framework, we can also minimize the likelihood in order to refine the position of a source. And so when we do that with a convolutional statistical model, we find that we are able to obtain a better estimate of the flux and also a better estimate of the position of synthetic sources. So now these are some detection maps comparing several models. What we see is that for ASA method for ASA it works generally better than ADI, and the proposed method is generally a bit better than PACO, and sometimes also better than MODEL&CO when in ADI. So yes, this I think I will skip a bit. And also a last advantage with this framework is that we can, since the first part is also is a statistical model very similar to PACO, or that is compatible with the framework of PACO, we can use it in order to do detection of exoplanets on multiple epochs. So the team that did PACO, so Olivier Flasser, they also worked on a framework to combine several epochs, so several observations, to improve the signal to noise ratio of an exoplanet. And so basically to make this method work, you need the output of PACO. But what we can do with our method is to, instead of doing giving the output of PACO to this multi-epoch detection framework, we can give the output of our model and then combine it to have an estimate of the SNR on multiple epochs. So that's what we did here. We can see that we are able to detect some existing exoplanets with a better SNR. So yeah, just to conclude on ExoMind. So we still have a model that is able to leverage a full data set of observations, because we have still some learnable components into the statistical model. So it has the same advantages of MODEL&CO. We can also do the calibration similar to MODEL&CO. What we added in this model is the multispectral correlation. So with a similar way as PACO. I can detail that a bit further, but it's not the main point. And also we can obtain a refined astrometry and characterization, which was not the case with MODEL&CO, and we can also include it into a multi-epoch detection framework. So just to conclude on this talk, I think the main points are that we can leverage a database of observations to improve post-processing algorithm, but we cannot just apply any deep learning architecture. It needs to be driven by the insight of previous methods. So in this case, what worked well was modeling the correlation at the scale of patches, and that's the same insight that we use to design the architecture of our model. And also, what's very nice with deep learning models, or at least with MODEL&CO and with ExoMind, is that you can apply them at scale, because there is no hyperparameter tuning for each observation. So you can just apply it on a lot of observation, and yeah, I think it's quite a nice property of this algorithm. Yeah. Yes. Okay. So thank you, and if you have questions, I will take them. Thank you.
Questions?
So going back to your sort of first model, and I think there's a general question I have, which is your machine learning models have the additional, like a whitening step in there, and show an improved contrast. Is this also applied to the sort of baseline PACO model with no machine learning?
So you mean deep PACO, the first one?
No, so like if you're comparing to like a non-machine learning model, is this step in that kind of data reduction as well, or is this exclusively for machine learning models?
No, we compare it here. When we compare it, we compare to PACO, which is not a machine learning model. So we compare the same with the same input, basically the performance that you can get with your model with the same input. So yeah, we don't compare only on a machine learning method.
Because if we're applying a step like that to the speckles, the contrast can improve because your noise levels have gone down potentially. And I'm just curious if that is the reason why, like, how do we quantify the improvement in contrast because of a reduction in the noise floor versus an improvement in contrast due to better detections?
So the question is where does the boost in performance come from? If it's because of the statistical model because of the learning that is behind it?
So is there like an SNR for the injected sources?
Well, the SNR depends on what you model, but generally, yes, what we do for MODEL&CO at least is that we inject sources but we also do it with DPACO, is that we inject sources in a given range of SNR, and the SNR is given by PACO in this case. So with DPACO, we inject sources that are not detectable by PACO, and also a bit above the detection threshold of PACO. So that it stays in a range of sources that are not impossible to detect or not too obvious.
Okay. So is it like a fair statement, or is this correct to say that the machine learning models detect sources which would be below your traditional detectable signal to noise ratio of something like 3 or something?
Yes. So this can be you can see it here more accurately if that's your question. So here we plot the output SNR of each method. So we can see that for the same source, we obtain a higher SNR with MODEL&CO than with PACO. And here the SNR are calibrated. So it means that for a given threshold in terms of SNR, for a given SNR, we have the same number of with the same probability of false alarm. So that every SNR means the same thing. And now we compare the output SNR.
Okay. Okay, thank you. Do you also have a false detection rate score somewhere? I might have missed it.
So the false detection rate is embedded into the detection score. So basically, this is the score of rock curves. So it's the area under the curve. So it's also aggregates false detection rate. But we don't have
like a percentage of detections that are incorrect, basically.
So to avoid that, we do calibration before, and so we don't really have a big number of false alarm once we have calibrated the SNR. So to calibrate the SNR, we take a lot of observation with no sources. So to ensure that there is no sources, we shuffle the frame, and then we compute the detection map on all those observation without sources, so that we can compute the number of false alarm per unit of SNR, and then we can inverse this curve so that every SNR means the same thing as for Paco. So yes, I would say that it's not really it's embedded into the detection score, the probability of for surround.
Okay. I have a machine learning question. Can you, on your loss function for the first Paco model, can you kind of describe what it does in words for someone who doesn't know what that is?
Okay, I will try.
Yeah, that function there.
Okay. So if my memory is good, I think it's I think that yeah, I think it tries to minimize on I think I'm not entirely sure what is the meaning of each term, but basically the general idea is to you have your detection map with some pixels that are turned on where there is a source, and some pixels that are turned off when there is no source. And so the issue that you usually have when you try to fit a model like that is that you have a lot more pixel where there is no source than pixel with source. So you have an imbalance in the labels. So what this loss does is that it corrects this imbalance of labels, so that it's easier for the model to learn. But I'm not entirely sure on the top of my head of where the formula comes from, but I know that it's related to the imbalance of positive and negative in the data.
So is it effectively comparing, is the pixel correctly assigned as source or not source, and normalizing for the discrepancy in the number of source and non-source pixels? That's the difference it sounds like it's doing. Okay, yeah, thank you.
But what it's not doing is to take into account the difficulty of the source. So a source that is very difficult that is not easily detectable will have the same will incur the same loss as a very easy source. So yeah, that's not taken into account into the loss.
Okay, thank you. That's everything I have.
Any people on Zoom have questions? Okay, then let me ask a question. So you're thinking about the, how to say, the interference of the machine learning model, like explain why it could detecting the characterized in the image.
So what's the impact of the machine learning model on the image?
How to say, just like, do you thinking about how the CNN or could work for those detection, like the attention map?
So what the CNN does basically is that when there is some artifacts that are not captured by the statistical model, it will be seen in the white-end data. So there are still some pattern in the white-end data that come from the fact that everything is not captured by the statistical model, and so the CNN is operating at a larger spatial scale, at the scale of the whole field of view, so that it's able to take into account those non-local correlations, if you will, And so that's what's helping in this case the detection of the source. I don't know if that answer your question.
Mm. If no more questions, let's send the speaker again.
Thank you.
Thank you.